All right, so this problem is in your notes packet. From the top of a 120-foot building, a ball is going to be thrown at an angle of 20 degrees with an initial velocity of 75 feet per second. So this up in here would then be my parametric equation that we would use for this, and there's the graph of it. From that, then we're going to ask these 4 questions. So the first question is, what is the height of the ball after 1.5 seconds? So I can do that question in one of 2 ways. I could go back to my graph, and I could say, come on now, come on, graph. I could go back to my graph here now that I got it working, and I can trace that, and I can trace it till I get a t-value of 1.5 seconds. Okay? So I could go, 0.1, there, keep going. 1 second, 1.5 seconds. Okay? And so it is asking, what is the height of the ball after 1.5 seconds? It would be 122 feet, approximately. Algebraically, height is based off of the y component, or the y part of my parametric equation. So if I wanted to know the height of the ball after 1.5 seconds, I would plug 1.5 seconds into negative 16t squared plus 75 sine of 20 degrees times t plus 120. So if I plug in 1.5 seconds here, and I plug in 1.5 seconds there, I would get something that looks like negative 16. I'll switch out just my, so let's not make it so much noise, times 1.5 squared plus 70, oops, put that instead of parentheses, plus 75 times the sine of 20 degrees times 1.5, then plus 120. And I get 122.477. So that's how we can find heights anywhere. We can plug whatever t value is into that function. Next question, when does the ball hit the ground? Well, algebraically, or excuse me, calculator-wise, you gotta get the right words here. Calculator-wise, I could take my trace here, and I could trace it on down, try and get when that ball hits the ground. But, as you can see, it's not necessarily always exact. So, somewhere, it's like the question was, when does the ball hit the ground? Well, it's somewhere in between 3.7 and 3.6 seconds. So let's try that one algebraically. So algebraically, when does the ball hit the ground? Well, the balls can hit the ground when the ball has a height of 0 feet. So I'm going to set my y component, or my y part of my parametric equation. I'm going to set it equal to 0. Now, I know that I can't factor this because of the sine of 20 degrees. But I can use the quadratic formula. And I can say that negative 16 is my A. 75, oops, I guess I forgot a plus sign right there. 75 times the sine of 20 degrees is my B, and 120 is my C. So I can plug that all into the quadratic formula, and I could say that T is going to equal the opposite of B plus or minus the square root of B squared minus 4 times A times C all over 2 times A. And I can plug that into, with the graphing calculators, it's nice. I'll show you how. I'm going to store my negative 16, oops, excuse me. I'm going to store negative 16 as A. Come on, A. Why did, I'm going to store negative 16 as A. Then I don't have to keep typing that in. I'm going to store 75 times the sine of 20 degrees. I'm going to store that as B. And then I'm going to store 120 as C. And then I can just simply type in the quadratic formula. Quadratic formula is the opposite of B plus, I can't do plus or minus, I gotta do plus here. I'll do plus and then I'll do minus, times the square root of B squared minus 4 times A times C all over 2A. And I get negative 2.5191 seconds. Well, that's when it was back in time. That's not the one I'm going to use. So then, let's do, oops, here. Just go over here and use the keyboard. It's much faster. I can copy that down, and I can just change this to a subtraction sign, and I get 3.65513 seconds. So that's algebraically how then I would solve for when does the ball hit the ground. It hits the ground at t equals 3 point, now I forgot what it was already, 65513. So we put that in.
You see they changed it.
So the next question, how far away from the building does the ball hit the ground? Well, we know now what the time frame is of the ball hitting the ground. So how far away, that's a horizontal component, so that is the x part of the parametric equation. 75 cosine of 20 degrees times t. So now we need to take our time, that how long it takes for it to hit the ground, and plug that in for t there, and that will give us then our how far away it hits the ground. So 3.55 or 3.65513, it's the last one that I have in there, so I can use the answer function. So I can say 75 times the cosine of 20 degrees times my answer, and I get 257.602 feet away. And the last one is, what is the maximum height of the ball? Well, if you notice that the graph is a parabola, and the maximum height of a parabola would be at the vertex. So I would need to find the vertex of this parabola. And I can do that in one of two ways. I can remember that the x part of a vertex is at x equals the opposite of b all over 2a. Or I could take these two time frames when the ball hits the ground, and I could take the average of those two. Okay? So I can do here the opposite of b divided by 2a. Oops, should have done that way. And I get 0.801. And that is the time that it takes for it to get to the maximum height. So this would be 0.80161, if memory serves me right. Yep, 80161. That number was right down there. That's kind of peeking out there. Okay. So that's my time frame to get to the maximum height. So then I could put that time into my y part, negative 16t squared plus 75 sine of 20 degrees times t plus 120. And now I can substitute in for t there, and I can substitute in for t right there. So I can say here, negative 16 times, that's my answer. I want to square that. Plus, well, that 75 sine of 20 I had saved on my calculator as b. That needs to be multiplied by my answer. And then I need to add that, oops, excuse me, corrections. And that gets me 130.281 feet. So that is how we can find all of those answers to those questions using algebra.